Hello everyone. So we are going to start the next part of the colloidal dispersion. So the next part of colloidal dispersion, it is your kinetics. Kinetics of colloidal dispersion. Now, if we say the kinetics, the first and foremost thing it is the Brownian motion. So the Brownian motion. So what is the Brownian motion? There should be one question in your mind, that what is the Brownian motion? If we consider, suppose this is to be a vessel, right? This is to be a vessel. So in this vessel we are having the dispersion medium, right? So the dispersion medium is there. Suppose this is the dispersion medium, right? Now if we put some dispersed phase in this medium where their size it is in the colloidal range, what they will do? They will show some Brownian motion. By virtue of the definition, Brownian motion means the rapid and random bombardment of particle in different way. Suppose if I again consider this condition, then what will happen? Suppose in this particular area, here there are different particles are there, right? Not this particle, suppose it is moving in this direction, it will move in direction, this is moving in this direction, this will move in this direction, random movement. They will have random movement, they will hit one another. So this is known as a simple bombardment. So the thing is that the Brownian motion, it is characterized by, if somebody asks you what is Brownian motion, then you should say that number one, it is having random motion. The Brownian motion means it will have random motion. This is not a directional motion. And the erratic motion of the particles, it is shown by particle up to 5 micrometer. Up to 5 micrometer the particle may show the Brownian motion. Now the thing is that how we can reduce this Brownian motion? Simply by increasing the size. Increasing the size. If we increase the size of the dispersed phase, I repeat, if we increase the size of the dispersed phase, then the Brownian motion can be hindered or can be stopped. Or apart from that, we can use any viscosity inducer. If we add any viscosity inducer to the dispersion medium, the viscosity inducer will hinder the movement, the random movement of the particles. Got it? So now the next concept of the colloid, it is the diffusion. So what is diffusion? First of all, let's discuss what is diffusion. See, by definition, diffusion means the transfer or movement of molecules from a region of higher concentration to a region of lower concentration. So means if I have, suppose there are two compartments, right? There are two compartments, and these two compartments, they are been divided via arbitrary wall, or suppose a virtual wall. So this compartment it is having a higher concentration, and this compartment is having somehow a low concentration. So the system, they always try to attain the state of equilibrium in this world, right? All the system, they want to attain the state of equilibrium. So what will happen? The molecules from the region of higher concentration, they will always try to move to the region of lower concentration, thus to equate their concentration, right? So now there is an equation of the diffusion. So as per the equation, we know dq is equal to dq, it is the rate of diffusion. dq is equal to minus y, as because the concentration is decreasing, right? dq is equal to minus ds. ds, it is the coefficient of diffusion, dot dc by dx. This is the amount of diffusion taking per unit area multiplied by dt, it is the time. So this is the equation. If somebody asks you what is diffusion coefficient, diffusion coefficient is equal to the rate of diffusion when the rate of diffusion is unity per unit area per unit time. Clear? I repeat, the diffusion coefficient, it is the rate of diffusion when the rate of diffusion is equal to unity, that is per unit area in per unit time. So this is the diffusion. Now the thing is that, you see, in this concept of diffusion, the colloidal particles, they can be analyzed. As we have already discussed regarding their analysis, the colloidal particle in the form of diffusion, whenever the colloidal particle will undergo the state of diffusion, we can analyze them for three basic parameters. Number one, particle size, right? Number two, shape of the particle. Number three, molecular weight. So these three attributes can be particle size, shape, molecular weight. These three attributes can be easily studied in case of the colloidal particle whenever they undergo the process of diffusion. Is it clear? So we are going to the next part. Now the next concept is that as per two scientists, Sutherland and Einstein. As per Sutherland and Einstein, we can determine, I have already discussed you, we can determine the radius of a particle. Then we can determine the radius of a particle. Moreover, the molecular weight of a colloidal particle. Now how we are going to do it? Simply we are going to have different equations. Just to determine the radius, we have a simple equation, that is capital D is equal to, I will tell you what is capital D. Capital D is equal to K, then capital T divided by 6 pi eta r. So this is the first equation. Just remember equation number 1. D is equal to KT divided by 6 pi eta r. From here, this r, it is the radius of the colloidal particle, right? Now this equation can be again modified. This equation can be again modified as D can be also written as D is equal to, in case of K it is the Boltzmann constant. I will tell you, K it is the Boltzmann constant. So here we can also use R, that is R is natural gas constant, right? RT divided by, this equation can be written as RT divided by, similarly 6 pi eta r, and as we are putting r here, so n, Avogadro's number, n will come in the denominator, n, this is the n. So by this equation we can determine the radius. So here K, it is the Boltzmann constant. It's a constant. R, this is what? We all know that R is the molar gas constant. T, it is the absolute temperature. Right? Eta, it is the viscosity of the solvent. Right? R, it is the radius. R, it is the radius of the colloidal particle, spherical colloidal particle. Right? And N, it is the Avogadro number. Clear? And it is the Avogadro number. And it is the Avogadro number. Now again, if we want to get the molecular weight, for molecular weight, earlier we have determined the radius, right? Now for molecular weight, what we can do? We have a simple equation. Simple. D is equal to, again, D is equal to RT. Natural gas constant, T is the absolute temperature, divided by 6 pi. Then we have the eta, viscosity. Then we have the Avogadro number, right? Multiplied by cube root multiplied by cube root of 4 pi and 4 pi capital N divided by 3 mV. This m, it is the molecular weight. I hope it is clear. D is equal to RT divided by 6 pi eta N, where R is the natural gas constant, T is the absolute temperature, where eta, it is the viscosity, N it is the Avogadro's number. Again here N is the Avogadro's number, M it is the molecular mass, V is the, finally this V is the partial specific volume. Just remember this V, it is the partial specific volume. Yeah. Okay, now the next concept, it is the concept of sedimentation. Sedimentation. So what do you mean by sedimentation? Simply let us consider a condition. Suppose this is a vessel consisting of water or any fluid. Then this is a vessel, so it is having some medium. Now whenever a particle will come to this vessel, it is going to traverse this whole path. It is going to traverse this whole path. It is going to traverse this whole path to settle down. Right? So the thing is that, see, this particle will have its own density, right? The water or the medium, it will have its own density. So as per these density differences, we do have one law. This law, it is known as the Stokes law. So what Stokes law used to say? Stokes law. As per the Stokes law, the rate of sedimentation V, it is equal to 2R square, right? Rho minus rho naught. I will tell you what is rho minus rho naught into G, specific gravity, divided by the whole divided by N eta. Clear? So here you see R, it is the radius of the spherical ball which is going to settle down, or the particle. R, it is the radius of the particle. Right? Now you see rho. So this rho, it is the density. This rho, it is the density of the particle. This rho, it is the density of the particle. Whereas this rho naught, this is the density of the medium, that is the water, or whatever the medium it is there, the fluid, the dispersion medium. Rho naught is the viscosity of the dispersion medium. the specific gravity, and here rho, it is the specific density of the sphere. Rho naught, it is the specific density of the medium. So V, rate of settlement, V, or the rate of sedimentation, V is equal to 2r square. R, it is the radius of the particle. 2r square within bracket rho, it is the density of the ball or the particle. Rho naught, it is the density of the medium, right, divided by n eta, it is the viscosity. Clear? Now you should know that all the particles, they obey the Stokes law, but there is a limit. There is a limit, and limit is there. All particles will follow the Stokes law up to a size of 5 micrometer. Up to a size of 5 micrometer, they will follow the Stokes law. But the thing is that if the Brownian motion, it is more. If the Brownian motion, it is more in such a condition, suppose a solid particle is trying to settle down through a liquid, if the Brownian motion is more, then the Stokes law will be less, because the Brownian motion will will nullify or cancel the specific gravity or the acceleration due to gravity. Thus, it don't allow, the Brownian motion will not allow the particle to get settled, and thus it will not follow the Stokes law. So in such cases, if the Brownian motion is more, in such cases we have to apply some extra energy. For example, using ultracentrifuge. We generally use ultracentrifugal machine, right? Ultracentrifuge is used to what? It is used to sediment the particles. So if the Brownian motion is high, then the particle will disobey the acceleration due to gravity. In such cases, we have to use the ultracentrifuge. So that's all from this part of the colloidal dispersion. I hope you like this video. If you just like this video, just press the thumb icon. You can share this video, then you can subscribe to my channel. Thank you once again.